Hey folks, we're looking at Haxl. It's a Haskell library developed by Facebook, which I think is still called Facebook, although they're part of the Meta conglomerate now. And they do Haskell-y things. They came upon my radar because I was looking for a library that does things like single flighting outgoing requests for an HTTP client. And I was going to write my own, but it seems like Facebook wrote one, and I thought it would be good to check out what some well-written Haskell looks like, because I certainly have no idea what I'm doing Haskell-wise. So let's peek under the hood, beneath the kimono, if you will, which you shouldn't, but that's what we're doing. We can read about what it is. It's a Haskell library that simplifies access to remote data, such as database or web-based services. And you can batch multiple requests to the same data source. That should be the single flighting I was talking about. You can request data from multiple data sources concurrently. That doesn't seem so unusual. You can also cache previous requests. It's nice to have built in, and you can memoize computations. Hello. Whoa. Not so much of a legend that I can't correctly do this. There we go. Is this going to work? Or Chamorro says, man, you are a legend. You read so much repos in and out, and your neurons will be like Arnold Schwarzenegger. I hope so. My goal in life is for my neurons, or my muscular neurons, to be like Arnold Schwarzenegger. It seems like he's had a pretty enjoyable life. Okay, and you can memoize computations, which is good. These are all good things to have in a client. I'm sure that these are, I don't know, people must use them in other languages. We have fun with Haxl. The story of Haxl. It explains how Haxl came about. That's, I guess I will add these to Wallabag to read them later. Although I'm not sure you usually need a description of why you developed the package. You know who I blame? I blame, what are they called? TED Talks? TED Talks told everyone that they should tell their like personal story, which is like the inverse of what they tell you in other writing and communication things, which is that you shouldn't tell the story of how you came to a conclusion. You should just say what the conclusion is and then add details later. But that's where we are. Okay, so there's the Haxl thing, there's examples, and there's tests. Since I don't know Haskell very well at all, and since I'm intending to use it, I may look at the examples and the tests, which I sometimes do and sometimes don't do, kind of depending on whether I expect to actually understand what I'm doing if I were to come to use it. I'm realizing I have my coffee, but not my water. Hopefully this will be okay. Okay, and then in the Haxl folder, we have core and data source. And I'm guessing core is going to be the coolest. I'm guessing these two, core and prelude, are going to be small files that mostly export stuff and import stuff. And this does seem to be the case. Although prelude has some, maybe some utility functions like mapm_, which I don't know why they need to implement their own. Maybe they just are not wanting to, no, here we go. I'll read this in a second. So I will open Prelude. I will not open Core, but I'll open these two folders. And let's just get to like looking a little bit at what we have going for us before I get to that Prelude comment. We have call graph, which, first of all, let's open fetch. Fetch seems important. Memo, I'm going to guess, is related to memoization. Parallel and profile and monad. I guess I'll go with monad. Run might be the thing that says like actually kick off this thing. Stats is probably, I'm going to guess, for keeping statistics about requests, as opposed to like telemetry for the package itself. Show P, this should be just like some maybe pretty printing. I don't know if I open profile. I don't know if I need profile. But now that the other things are opened, I will do call graph, which might be super cool. It might not be super cool. Data cache, no, data source, data cache. Well, I think ignore exception, but I'll open memo and monad. And I don't remember if I opened request store, but I'll just do it. There's no harm. And that was data source. Let's open core. Wait, no, that was core. Let's open data source is what I meant to say and do. And we just have concurrent IO. In fact, that's what this thing is. I guess we just might as well open it. There's nothing else to do. And that brings us to prelude.hs. And we get some comments, some useful comments. Support for using Haxl as a DSL, domain specific language. I assume this module provides most of the standard prelude, plus a selection of stuff that makes Haxl client code cleaner and more concise. Those are values I also share. So most of the standard prelude, I'm guessing they mean, I don't know much about using DSLs in Haskell. I'm guessing they mean that the standard prelude, as in the normal thing that is the like the standard C library, but for Haskell that's included in GHC. They're replicating those commands in some sort of Haxl-y context, maybe for DSL stuff, but I'm not entirely sure how to parse this. Plus a selection of stuff that makes Haxl client. Oh, we already read that sentence. Okay. We intend Haxl code to import Haxl prelude with some @ symbols. And I'm guessing maybe the @ symbols are not part of like how you literally import it. I'm guessing they are part of the, what is the Haskell document thing? Package? Is that the document server? I'm not familiar with Haxl. Yeah, neither am I. Coward, are you familiar with Haskell, the language? I'm guessing these @ symbols are like going to linkify the documentation as opposed to being part of the Haskell syntax. Although you never know, because with Haskell, you can just define arbitrary syntax, and that's how it is. That's not literally true, but people will define different operators that are like ASCII characters. Haskell, the language you know about. Okay, that's good. Then I think we're basically in the same boat. So here's Haxl prelude. And we've got some stuff like gen Haxl data fetch, data source memo, memoize 2. And these are, I think, just things we're exporting. Although I've never really seen them side by side, but that's fine. And then some applicative stuff, some map m and map m underscore, which I've used. I don't entirely remember the difference. I think maybe map m underscore does the mapping but ignores the result. And then sequence and sequence underscore, which I am not sure what those do. I don't think I've used them. I've used similar functions probably in R. I'm guessing they're somewhat similar. They operate on some sort of sequence. Maybe they sequentialize operations. We'll find out, I guess. And then filter m, fold m, for m, and for m. These are like filter and folds for the monadic context. And I'm guessing, again, that the underscore here means that we ignore the result. And then foldal prime is, I can't remember, is left fold the one that's implemented kind of wrong in Haskell? In Haskell? I'm not sure, but we'll come back to these in a second. Sort, monad, join, and them. And by a second, I mean now. So let's look at let's just try this. Foldal, folder, and foldal prime. Let's say we want to calculate the sum of a very big list. Okay. So fold L, the problem with the chain of pluses is that it can't be made smaller or reduced until the very last moment. So these fold functions, they build up a lazy computation, like a lazy fold computation, and then that can be a problem, I think, memory-wise. The reason we can't reduce the chain is that it doesn't contain an expression which can be reduced, a redex for reducible expression. And you can introduce a redex, and then where's foldal prime? Foldal prime, we've got seek, which I think forces non-laziness. Is that right? Seek is a primitive system function that when applied to x and y will first reduce x and then return y. The idea is that that y references x, so that when y is reduced, x will not be a big unreduced chain anymore. Okay. That's kind of similar, I think, to at least how I intuitively understood it. And foldal and foldal prime are the same except for their strictness properties. Okay. And Coward says, for me, it's the kind of thing I keep around but never actually use. Yeah, it has limited. Whoa, I'm frozen. I like using Haxl. I'm not such a fan of its ecosystem yet. What are the chances I can unfreeze myself here? Give me a second. Okay, what we were doing, we decided that foldal prime was different from foldal only in the fact that it has different laziness properties. And then I wanted to look up map m versus map m underscore. I went to Hackage, but I meant Hoogle. Hoogle is the place to be. And map m underscore, I guess, returns an m of nothing. And this map m returns an m of tb. So I think that is basically the same, except we ignore something about a return value. Map each element of a structure to a monadic action. Whoa. Evaluate these actions from left to right and ignore the results. Okay, and so I'm guessing that this convention is general, so that sequence underscore will do whatever sequence does, but ignore the results. So sequence returns an MTA. Where's search here? Yeah, okay. But we still don't know what sequence does, or at least I don't. You may, if you do Haxl. Sequence, find it, do it. Evaluate each monadic action in the structure from left to right and collect the results. That sounds a lot like 4M. But that's in a different thing. Okay. You guys keep your God's word. All right. Thank you, Coward. Thanks for stopping by. Okay. So that tells us, map M. And then 4M is, I guess, for traversables. These are just different ways, I think, of doing conceptually the same thing. So map M, map each element of the structure to a monadic action. So we've got some structure. We have a map from A into a monadized B, and whatever a T of A is, maybe a traversable, and we're going to get an M of TB. Structure to a monadic action, and then evaluate them from left to right, and then the sequence says, evaluate each monadic action in the structure from left to right. So we're still using the word structure and monadic action. But now I guess we have a structure of monadic actions. We have a T. Whoa, my cursor got big. I don't know what I did to do that. But we have a T of M of A, maybe a traversable of M of A. But there's no condition here other than that M is a monad. I'm going to map it to an M of T of A. And we get results. So if we call sequence on right of 1, 2, 3, 4, then we get right of 1, right of 2, right of 3, right of 4. And right 1, 2, 3, 4 is a T of M of A. I'm guessing maybe the monad here is list. So we have, maybe T is not necessarily traversable, but T, I guess here is right. M is list, and that's going to give us a list of either left or right things of integers in this case. And a sequence of, whoa. And if we remap it, we take the result here, this is just the same, right? And we've got a list of right. Then we get a right of lists. I guess maybe that's because either is itself a monad. Otherwise, what? You're using either as a monad. Okay. And what about map M? Where did map M go? I thought it was right above sequence. Map M. Here's map M underscore. Let's do map M without the underscore. Whoa. No examples. Map M is literally a traverse with a type signature restricted to monad. Okay. So it's basically the same as traverse. And traverse, as if F is applicative, then, and you have a function from A that produces an F of B, and you have a T of A, then you're going to wrap the T of B with F on the outside. So if you traverse just 1, 2, 3, 4, you're going to get just 1, 2, 3, 4. Is that good? So in this case, maybe just isn't maps like int to maybe int, and you're calling it on a list of ints, and you're going to get maybe of a list of ints, assuming T is list and F is just. On the other hand, if you traverse with the identity, then identity is this, I guess. And we've got a list of maybe things. And we're going to get back what? Wait, where did I go? Here. No, I see. Okay, so I think right 1 is F of B. So we get right on the outside of the integers. So T, I guess, is the identity. Is that right? Something like that? I'm not sure. But that's, I guess, that's what traverse does, and probably seeing a lot of examples is what will help us orient ourselves, but we're not doing that right now. We're looking at Haxl. Okay, so what else do we have? We have some if-then stuff, which is probably not so fun. We've got this infix R. This is, I think, defining an infix operator. Maybe this is just priority. I don't know. Let's look at Hugel again. Infix R. Fixity direction. Maybe R is associative on the right. The associativity of an operator. Where's the definition here? Let's just look here. How does infix work? Let's ask ChatGPT. Tell me about infix R in Haskell. Answer succinctly. Okay, it's right associative and it's got a precedence level. Perfect. And that's good. That's exactly what I wanted to know as quickly as I wanted to know it. Don't do that. And let's ask it about this traverse example, because I feel like I wasn't quite getting where I wanted with it. Okay. So we'll copy all this. Let's ask, wait, what? Let's ask, I guess, Gemini. So tell me about the traverse example with the ID function. And we'll paste it here. The user wants to understand. Does he? So ID is the function A from F to B. Okay, that's what I was thinking. But what was tripping me up then? So ID takes A to F of B. So F of B just has to be A, right? And in this case, ID acts as the function. Blah, blah, okay, the list. So T is the I guess like the list monad. We have a T of A, and the elements are right one blah blah. So traverse applies the ID function to each of these elements. So we get right one, right two, etc., etc., and then traverse then collects these results because traverse works with an applicative context. In this case, either it knows how to combine the right values. Right values are combined into a new right value. Since they're all right, we get, that's how it pulls it out. Oh, okay. So it must, it's like talking as if it has some knowledge of the underlying monad, which I'm not sure is the case. But here, this is a list of A, and we're going to get ID of a list of B, but B is A. And what was... A should be a... no, I don't think I understand. Okay, so here... so A FB is identity. So F of B is A. Okay, so it says, it's saying I'm confused. The function signature is ID from A to A. When you traverse ID right one, right two. It needs to unify the type of ID with the type of the first argument to traverse, which is A to FB. To make A to A to FB compatible, the type checker performs a process called unification. The only way for A and FB to be the same is if F is the identity functor. Yeah? A to A becomes A to identity A, therefore F is unified with identity, and this makes B the same. Yes, that's what I said, right? Okay. I think it's saying it agrees. So if F is is identity, then T is list. Then on the right hand side, shouldn't we have a list of A's? And A is Gemini is telling me I'm correct, but I don't think I can be correct. Okay, but in the example, it's returning a maybe of list of ints, not a list of maybe ints. Okay, it points to a critical detail. I told it to be succinct, and it doesn't seem to be doing that. It seems to be doing all of this like critical detail stuff. I told it to be succinct in its in the configuration, not in the prompt. So just 1, 2, 3, a function just is being used, but not ID. Okay. Unifies the types A to FB, becomes A to maybe A, which means that F is maybe. Isn't that different from what you told me before? Okay, if F is maybe, then I guess I believe it. This is different from your ID. No. Okay, I'm not going to talk to it anymore about this, but well, yes, I am. I'm just going to remind it what the example is, because it seems to be yes, that is what I'm asking. Something about type difference. Yeah. Okay. To the list has the type either E integer, right? Oh, I was saying maybe, but I meant either. So either. So yeah, T is the list type. And A is either whatever something is or integer. Blah, blah, blah. So this, since A is either E integer, the function ID must operate on either E integer, right? The types match, blah, blah, blah. This means that f of b is either E integer. F is the either of E function, B is an integer. The final result, it will combine the results using applicative instance for either. So what is A then? Okay. I don't know what's going on. Anyway, so I'm still confused about that. I think I'm just going to cut that out when I edit this video, because I'll go back and ask it. But where is it? What's going on is I'm looking at the Haxl source code, and I've gone down a rabbit hole here trying to understand this example from Traverse. So if the ID, the first argument has to be the ID function, which means that this is a list of. No, I am going to ask it about it. And then I'm going to finish up with going down this rabbit hole. So in this example, I think that maybe I'll just ask a different. I'm asking Flash. That was my mistake. That was a mistake. Let's try this again. I'll cut all this out. Usually I use Emacs. I sometimes also use other IDEs depending on the language, like Android Studio, or very occasionally I use VS Code. Okay. Effectively flips the structure, pulling the applicative context either, in this case, to the outside. Okay, so I understand that conceptually. So traverse ID, the structure T of A, the input is a list. Yes, where each element A has a type either, string, or int. So I guess we don't know what the other one is. We just know that it's an either. So T is the list and A is either string or int. Yes. The function A to FB is ID. Since ID has a type X to X, the input A must be the same as FB. This means that either string int is our FB. The applicative context F is either string. The resulting type, inner type, is B. What? So I guess it's saying that it's doing like pattern matching. It says, I think it's basically saying it's doing pattern matching. It has to, I guess, find an applicative, and the only one in sight is either. And then the traverse evaluates each action and collects the results. This applies ID to each element, which changes nothing. ID of right one is right one, etc. Then uses the applicative behavior of either to combine the results. Okay. Oh, well. I see the mistake I'm making. Okay. So the mistake I'm making is there's pattern matching going on. So A and F of B are identical via the identity function. I thought F was the identity like functor, which was the result of my confusion. Okay. So that's good. Have I tried Vim though? You've not tried Vim. I've tried, you know what? I use Vim all the time for little edits. Anytime I have to Vim starts up faster than my full Emacs config. So I have two quick editors. One is an Emacs client and the other is Vim. But for example, sudo vim works better because I don't have Emacs config set up for the admin user, or if I'm SSHing into a unfamiliar box, I use Vim as my kind of default small editor, but I haven't used it as like a full development environment. I'm not opposed to it. I use Emacs, and this is not really a reason to switch. Not yet, anyway. Okay. All of that, which mostly I will remove, because it's not that fun to watch me be confused. Okay, so now we're back here, and these are operators. So I think that these should be what were defined here. So these are infix operators. We have neither R nor L, but these two are right associative, and they have, I guess, priority 3 and 2 respectively, and these ones have priority 4. I don't know if higher is more priority or less, but I guess that doesn't really matter for us. We also have this if then else, and this is all just Haskell prelude stuff. Here's an equality constraint. Oh, no, the equality constraint is necessary to convince the type checker that this is valid. We have this if then else. If we have a gen Haxl thing, maybe that means generated. If we've got two gen Haxl things, then something is true. We're going to call if then else FB, TE, do, etc., whatever that means. We'll ignore that. Instance num A. I guess this is saying this is a type of number. Like it implements the num interface or something. And if we're going to add together two gen Haxl UWAs, then we're going to call lift A2 on plus. What lift A2 is, I don't know. Lift, it's somehow lifting something A. I don't know what A is. Maybe lift, I don't know. But lift, I think 2 is probably the arity. So we are like lifting, I guess, the Haxl stuff up to a type that projects down to it and where plus is well defined. And we're doing that for all of these. It's kind of like, maybe a little bit like unboxing. From integer, I guess mainly just works. Abs and signum and negate all work as usual. These are unary operators, so we just call lift A instead of lift A2. And then we have fractional stuff. We can get the reciprocal and divide. So somehow gen Haxl of UWA is like a real number or something. But I don't think we've seen what that type is. I don't think we've seen the definition yet. And then these are like ordering. So one can be less than each, one can be less than another. They can be less than or equal, etc. So we have an ordering on whatever the gen Haxl things are and some Boolean operators. And then we have applicative traversals. We don't want the monadic map M because that doesn't do batching. Okay, so the map M should just monadically map over like a list or a tree, but it doesn't like batch up the elements of a list, I guess is what it's saying. There doesn't seem to be a way to make data traversable map M have the right behavior when used with Haxl. So instead we define map M to be traverse in Haxl code. I thought map M already was traverse. But what do I know? Okay, so they're just, this is just the same stuff. So T is now traversable. I guess the difference is the original mapm definition doesn't require T to be traversable. It's implied by naming it T, but it's not a requirement. And so that's what we're doing. So, and then for M is we're just going to flip mapm. This all must be well known, I think, to Haskell programmers. And we have this and then function. Okay, so, and then catch any. This is some sort of error handling, but what kind, I don't know. All right, that was, I guess, mildly informative. Somehow they're going to build up a structure that has ordering and integer properties. What the structure is, I don't know, but it's something. It's something. So let's find out. I guess the next thing to do is let's just find out what gen Haxl is. It takes 3 arguments and produces some sort of integer, I think. Here's parallel. Type Haxl is equal to gen Haxl of nothing, nothing. Main? No. New type, here we go. Monad, core monad. All right, so gen Haxl of UWA is gen Haxl, and we've got unhaxl, which end, is that like an environment? Given an environment with U and W, we're going to return an IO result of UWA. And I'm guessing, I'm hoping this comment will tell us what these things are. So the Haxl monad, which does several things. It is a reader monad for env. So it's going to read env in a monady way, which contains the current state of the scheduler. Okay, so there's a scheduler. And remember, we're doing things like batching up fetch requests. I'm using this for a fetcher for my like read it later app. So there's a scheduler that has some state. I'm not sure exactly what the state is, but you can imagine, you know, as I was thinking about how I would build this, I was thinking, let's say that everyone, you know, there's a hot new article on I don't know what the hot websites are, but let's say not Medium. What's the one where everyone does their blogs? Let's say Medium. Let's say Medium. Let's say like something is just posted and 1,000 people add the same article within like 5 seconds of each other. You want to ideally fetch it once. So you're going to have to take all of those requests, put them in some sort of queue or structure so that you can at least answer the question, do I have multiple requests for this? And then once you're done fetching it, you want to be able to tell all the requesters that the result is fetched. And so that's kind of some of the state that would need to go into a scheduler, I would think. I don't know in practice how they do it. But it's going to include unfetched requests and the run queue of computations. And I'm not sure what sort of computations we're talking about, but it may be... And this may be for like database results where you need to do some post-processing, or it may be for like computing things like back off or whatever. Hey, bot eater. You crashed in late. Not that late, because I spend a lot of time just being confused. As is pretty usual, but I guess is more common in a Haskell repo. Okay, so the Haxl monad is also a writer for write tree. These can be used to do arbitrary logs from any Haxl computation. These are better than doing arbitrary I/O from a Haxl computation, as these writes also get memoized if the Haxl computation associated with them is memoized. Okay, so there's like a write, except it gets memoized. Since they're also logs, they probably also get like batched and stuff like that. Now, if this memoized computation is run again, you'll get the writes twice. Nice. It is a concurrency or resumption monad. I have no idea what a concurrency or resumption monad is. I am guessing it's a monad that enables concurrency in a kind of monadic interface. A computation may run partially and return blocked. Okay, so that's a little bit like coroutine-ish, in which case the framework should perform the outstanding requests in the request store and then resume the computation. So if you're blocked, you can return blocked, but I guess you can't say what you are blocked on. And so it's just going to do everything until you are, and just assume that unblocks you. And I guess like it has to know that when you return blocked, then it should hopefully finish the things it currently has in its queue. And if the queue is still filling up, it shouldn't keep like blocking you until all of the new orders are also done. You should essentially get like a place in the queue that you go at the bottom or whatever, and then that'll work. Okay. And then there's an applicative combinator, which looks like not the Death Star. It looks like the a TIE fighter. It explores both branches in the event that the left branch is blocked, so that we can collect multiple requests and submit them as a batch. Okay, and it contains I/O, so we can perform real data fetching. Haskell seems confusing. It is pretty confusing. There's a structure to it. I guess maybe one way to think about it is that it's kind of like Legos in a way, where once you get familiar with the Legos, they're easy to combine. Whereas if you have like C or C++, you can basically do arbitrary things. So there's less of a constraint that requires you to build reusable Legos. Hello, Hadi Mohammadi. How goes it? Okay, and so I still don't know what U and W are. And that's we just have this unhaxl thing, and it's going to read from the environment, I guess. Let's read on. So tell write is going to take a W thing. I don't know whether W is like something to write, if it's like a reference to a like a handle to something that does writing. But at any rate, we're going to take one of those and a gen Haxl U of write tree W and A. It's going to, whatever A is. I guess maybe A is like the return value. And W, I guess, is write the righty thing. And U is, I don't know yet. And tell write is going to call write dot sum write. Why does that work? I don't know. Where is sum write defined? Here's a write tree. A tree of writes done during a Haxl computation. We could use a simple list, but this allows us to avoid multiple mapends, when concatenating writes from two Haxl computations. Users should treat this data type as opaque and prefer to use flattened WT to get a simple list of writes from a write tree. And we also have this thing, this like semi-group structure. This is different from the, I guess, the TIE fighter with an asterisk in between. Although I don't entirely, oh, this is append. This is typically append in Haskell, right? Okay, this is like append whatever the righty stuff is. And flatten WT, we have this go function, which I think is often maybe used for recursion. We're going to call go on the empty list, where go WS is, and the bang means it's like whatever the word for the opposite of lazy. It's like greedily evaluated. Eager, I think, eagerly evaluated. And then if we call nil writes, we just get WS. Okay, so if we're called with WS and nil writes, we just get the WS back. If we're called with WS and some write of W, we're just going to build them up. We're going to prepend our list of W of righty things with the new thing. So this is like basically just like a list so far. And if we call it with merge writes of W1 and W2, we are going to first call WSW2, which is going to result in W2 then followed by WS. And then we're going to call this with W1. And so I think that's going to be W1, W2, WS. Is that right? I don't know. This function must be called at the end of the Haxl computation. Okay, so I think that's what's going on. Maybe merge writes looks a little bit unusual because it's probably not really meant for this interface. Maybe it's meant more for the tree interface. And this is just kind of like the way to linearize it. All right, I still don't know what U and W are. How can I find that out? W I feel like must be right. A is maybe like answer. I don't know. Here's a job list, a list of computations together with the IVAR into which they should put their result. An IVAR, I'm guessing, is like an MVAR. It's like a cell of memory. We'll look that up in a second. This could be an ordinary list, but the optimized representation saves space and time. So you've got data, job list takes a U and a W. And it's either a job nil, which is like no job at all, I suppose. And then, or for every A, we're going to call job cons, which should be like concatenating jobs, I assume, with the environment, the U and the W, the gen Haxl UWA, whatever this unpack thing is. Oh, okay. This is probably like stuffing it in an IVAR. And then this is recursive on the job list UW. So I'm not really sure what entirely is going on, but we can look up IVAR. Maybe like this. Is there a dumb constructor? I don't know. I don't know what that means. An IVAR is a write once variable, immutable variable. Okay, so we can write into it, and that's it. It provides a way to block on multiple variables simultaneously, resuming when the first of them is written. The module is careful to not create memory leaks and prefers to maintain good long-term memory performance than to be super fast. It should be reasonably fast, though. Okay. You can write to it once, and it provides a way to block on multiple variables simultaneously. Okay. I don't know where the blocking stuff is, but I guess that'll be good enough for me. So what are our options for finding out what U and W are? We could look more at more code. You don't need these two tabs. Here's fetch. Let's look at fetch. Implementation of data fetching operations. Most users should import Haxl core instead. This is a data cache result thing. Data fetching and caching. Again, we've got UWA. Maybe it's in the Haxl documentation. I'll ask ChatGPT in Haxl, what do U, W, and A stand for? So U is user environment. This type representing a user-specific state or environment. Okay, it might hold things like authentication, feature flag, config values. A is the result type. That I understood. It's not going to tell me what W is. Didn't I ask it about W? Okay, W must be the writing type. So U is user environment. Yeah, you don't know what you're talking about. Okay, so I'm going to guess that's what's up. So when we cache result, we're going to cache it with respect to the user, the type of result we get back, and something about writing, some sort of place to write it, I assume. And we can show a request, given a request and the result. Show functions for request and its result. Oh, this is just defining a type. I thought this was defining a function. Okay, that's fine. Here's cached with insert. Occasionally for tracing purposes or generating exceptions, we need to call show on the request in a place where we cannot have a show dictionary. Because the function is a worker which is called by one of the with show variants that take explicit show functions via a show rec argument. Okay, whatever that means. Some details about like calling show, I guess. And cache with insert, we're gonna for all RAUW. R should be the request, A is the return type, U is the user environment, and W is some righty thing that I don't entirely know. And I guess the data source is parameterized by the user environment and the result. So like a database, I guess, might have a certain kind of result, and whatever typeable is, RA. And we're going to return a function that takes a result and a return type, and it's going to return a string. And it says CNode. Okay, well, here's a standard result var. Make a result var with the standard function for sending the completion rec to the scheduler. Okay, so now we're getting to the scheduler stuff. Whatever result var is, presumably some variable that's going to hold the result. And we're going to sending a completion rec, I guess a completion request to the scheduler. This is the function. This is the function that will be executed when the fetch completes. Okay, we've got the standard result var. And for all of this stuff, we're going to return a thing that takes the environment, the ivar, whatever the proxy is, proxy of R, and we're going to return a result var of A, the answer type. Again, we're doing ivar stuff. We're calling make result var. Checking if, I don't really, I think /r is just, this is just defining like a lambda. We're checking if it's the child thread. Alex must be some sort of allocation stuff. If child thread, if we're in the child thread, then we're going to call get allocation counter. In the child thread, return the current allocation counter too for correct tracking of allocation. Okay, so we just need to track, and so we're just going to return the thread's allocation counter. Otherwise, we're going to return 0. And then atomically unblocking, whatever logic bug is doing. Logic bug, reading completions failed fetch, data source P. Maybe this is blocking if there is a logic bug or if there's a failure. And I guess if we're not blocking, then we're going to do, we're going to read the tvar on completions. Where did the completions come from? Somewhere. I don't know. And then we're going to write the tvar completions, passing in also the complete request, calling either to result on R. So R must be like an either thing. And we're going to uneitherify it. And we're also passing the ivar and the Alex. I'm guessing Alex, I think, is mainly for keeping statistics on the allocations. And then that's calling write tvar. So I guess by now we've written something into the tvar. And then we're going to decrement the counter as request is finished. So the request is done. So we decrement the counter. And if we're supposed to report outgone fetches, then we're going to call atomic modify IO ref, submitted request ref. And we're going to subtract from count map 1 somehow. And we're going to inline standard result var. So I guess this whole function is inlined, which seems reasonable. And I think if we like read through the Haxl, then what we're doing is probably totally sane. We're just mainly, this is like get stuff for statistics, maybe report stuff for statistics. We may block on stuff if stuff goes wrong. And we're going to read the completions variable and write to it, basically adding our result. We looked up ivar. I don't know what tvar is. Shared memory locations that support atomic memory transactions. Okay. Single letter type variables makes the intent confusing. I agree. I like how Elm programmers do when they name their type variables like their term variables. I agree with the single name variables. I don't understand the point. I think people kind of like it that they feel that it reduces cognitive noise if you always use the same convention, but the convention at least needs to be documented, well documented. And then, block like in my multi-threading. Yeah, I think that's what the blocking is. And then R, Brahmaditya said you can go to a function's definition by clicking it. Can I though? I don't. Somewhat. I think this is not the. It depends on like how much the repo is paying. GitHub, I think. It's Brahma. Okay, Brahma. Sorry. All right. So this is more or less reasonable, I think. And let's see what else we can understand. Log fetch, record the call stack for data, and then how calc failure. what? We've got some for all u rec now instead of r in A, some data source u rec. And we're going to, the function takes the u, which is the environment rec of A, and it's going to, and it also takes either some exception or the return type, and it's going to return a failure count, which makes sense because it's calculating the failure. And if you give it a write, so write should be the success condition, then we're going to return m empty, so basically empty, nothing. But if you have left, if you call write and what? I don't know what write of empty curly braces is. But if it's left of E, then we're going to do a case analysis. If it's a standard failure, we're going to call m empty of failure standard count equals 1. Otherwise, m empty of failure count ignored equals 1. But why m empty in those cases? Let's ask Hoogly Hoogle. You can, yeah, I can go to the package doc. That's true. That's true. It's a good idea. Although I find that Haskell, the package doc should be created from the code, I guess. But you're saying that I can use it to go to the definition. That's true. I also have tags set up, I think in Emacs, although I don't know if it correctly set up Haskell tags. Let's try this. Let's just, oh, I do have tags. So I don't know if they work in Haskell. Let's see. They more or less work. I don't remember what I was trying to find. But mempty is it's just identity of mappend. Okay. I don't know why we need to call the identity function for these cases at the bottom, but that's fine. Data fetch calls data fetch with insert. Performs the actual fetching of the data for request from a data source. Okay, so we're going to call data fetch with insert, and just, I think this basically is saying we're going to fetch it, but also put it into the cache. And we're calling show, or we have a show somewhere. Data fetch with show, and here's data fetch with insert. Performs the actual fetching of data for a request from a data source using the given function to insert requests in the cache. Okay, I guess this is saying if you just call data fetch, you can configure how you insert into the cache, but if you just call it with no kind of like fanciness, it's just going to use show to turn the result into like a string. I assume is what they're saying. And we've got the show function, the insert function. Whoa, where's the insert function? That must be the show function, and this must be the insert function. Okay. And the request. And we have this gen Haxl thing. Whatever this env, this I think is just a like a lambda notation. I don't know what the env at env is. Maybe it's like exploding the env so you can refer to its components more easily or something. First, we're going to check the cache. We're going to call cached with insert. Cached with insert. I guess maybe with insert means with configurable insert function or something. But again, calling with the same show function, insert function, the env and the request, and we might get a result. And if the result is uncached, that means we haven't seen it before. And we're going to call log fetch. And log fetch presumably will fetch while also logging. And we might be profiling, in which case we do some profiling stuff. Check whether the data source wants to submit requests equally or batch them up. Okay, so I guess that's up to the data source to decide. We're going to call blocked fetch on the request in the rvar which is now a new kind of var. Var. A random variable with some distribution. Okay, so we've got, we're called blocked fetch with the request, a random variable. I don't know if that's right. And we've got blocked fetch I, passing in fid, whatever her fid is. Fid is the part of the result of uncached. It might be a compiler. It might be. We can also just. I mean, you can generally ask the. You can also search for this stuff on an ordinary search engine, but I find that, like for things like Haxl, it's often hard to find a direct answer. So yes, it's a lambda function taking one argument. Okay, so the pattern is an as pattern, match the structure env as above, and also bind the entire value to the name env. So now you can use individual fields like user env and cache, etc. Okay, that's, I think basically what I said is kind of like exploding the exploding it so we can use the variables. Record wildcards. Okay. So we've got these two blocking things. One is internal, one is not internal. And we're going to set submit fetch to something. We're going to compute some stuff. We've got a scheduler hint on R. That's going to give us hint. And this is just the type. And I actually don't think I realized you could do a type after let. That's kind of useful. Scheduler hint state. State get, we're calling state get on states. We're getting the state. We're calling scheduler hint state on the user env. And the hint is what? Something of, it's either it's submit immediately or try to batch. So the scheduler hint is just telling you, like, should we batch? And if we submit immediately, we're going to call perform fetches, passing in the env with the list of blocked fetches. Maybe blocking is just to prevent abuse and stuff like that. And then if it's try to batch, we're going to call modify IO ref request store ref BS add request blocked fetch. Okay, so this stuff is just still like blocking information, or at least these two. And modify IO ref should be to like mutating an IO reference. And we're passing in, I guess, maybe this is the name of the variable where the reference is stored, some region of memory, and we're going to try to call add request on it. And then what is BS? This is a lambda. So this should be adding the request to the request store. I guess this just is taking a function. And so this is just telling it how to modify it. So I think this is just saying add the request to the request store. And then in either case, we're going to return blocked ivar, return ivar. Okay. I don't know what return blocked ivar is doing. But I think that the sort of thing it has to be doing is, I think somehow it says we're doing work and now we're not doing work. And that's kind of what's going on. And what happens here? Okay, we saw the two main things. Either you submit it immediately or you try to batch. And then if we're down here, then there's some data cache fetch fallback. If there's a fallback configured, try that, else dispatch the fetch. Okay, so when do we get down there? If the result is not cached, right? So if we're here, no, if we're up here and the result is not cached, that's when we actually fetched. The other case is data cache fallback. Okay. So I guess, I don't know what this is, but this is sort of, I guess, fallback you can configure that you get back in the cache, I believe, is where we are. And if you have that, no? Where are we? I think this is all for uncached. I'm not quite sure when we get down here, but there's this fallback thing, and if it's nothing, then we submit the fetch, and I guess we don't even try to batch. No, I don't know. Something, but I'm gonna, I guess, ignore this for now. But if the result of the cache lookup is cached, not fetched, then we've seen it before, but not fetched yet. We're blocked, so we don't have to add the request to the request store. Then we may be profiling stuff, but we're going to say we're blocked on the IVAR. So this is just, I guess, an assumption that we know that if we are reached here, then we are blocked. Because I guess that's just what cached, not fetched means. And then if we are cached and we've actually been fetched, then we just, I guess, return the end with the R. I'm not really sure what done is, but I'm guessing it kind of like does some sort of return with short circuiting. I do want to kind of see what this region of code that I wasn't really sure where it was lining up with. Let's look at it in Emacs so we can see columns. I'm not a huge fan of white space, a significant white space, but where am I? Let's say line 3 or 4. Oh, that's where it was. Okay, so this thing here, case res of, this is about column 4. Okay, this data fetch callback is column 6. So we've got this let block here. I guess if we're down here, then we are in the, we are uncached, but we haven't returned. And we return, I'm not sure. We should return. Oh, no, hang on. We're just defining submit fetch. Is that right? Okay, yes. This is just defining a function. It's not actually executing. And then we go down here regardless. And if there is no callback, then we just execute the function we defined up here. And if we have a data cache lookup decal thing, then we do some other stuff, which I'm mostly going to ignore. Okay, I feel like I'm getting a feel for what's going on. Kind of, not entirely. Let's see what else we can find. Cache request inserts the request result pair into the cache. Throws an exception if let's see. Duplicable cache request. Similar to cache request, but doesn't throw an exception if the key already exists in the cache. If this function is called twice to cache the same Haxl request, the first value will be discarded and overwritten with the second value. Useful, for example, for unit tests. Okay. Perform fetches issues a batch of fetches in a request store. After perform fetches, all of the requests in the request store are complete. Okay, so this, I guess, is pumping the queue until it's empty. And we've got this flag stuff. We're going to get the timestamp. I guess we're always doing some sort of tracing because there's no conditions around whether we're getting the timestamp. And if we are tracing, we'll do some stuff. And we're going to be in this let block. We're going to define this function, I guess. Apply fetch I BFS at blocked. So whatever I is, maybe just an index. And with some blocked fetch information, we're going to call get state on the states of the environment. If it's nothing, then we're going to return fetch to do of requests. Whatever the sync fetch is that has some map M of set error. And there's some like data source not initialized error handling. If it's just state, so get state returns something that's not nothing, then we're going to return fetch to do requests and some possibly statistics reporting. And we'll call wrap fetch and trace. Wrap fetch and catch, maybe for error handling, and then fetch state F, passing in the user environment. And then DS name is the data source name. And there's something about a proxy in here. And then for fetches, we're going to call some sort of zip function, like a monadic zip, calling apply fetch on, I had guessed that I was an index. That seems to be the case. This seems to be saying we're going to grab all of the jobs. We're going to like enumerate them, and those will be our set of fetches. And then we're going to call schedule fetches, passing in the fetches that we got by zipping it up, along with the submitted requests reference of env. So I guess in the end, we store some things, including the submitted request reference and the flags, which I guess we get from the environment also. And we get the T1 timestamp. And then the round trip time we compute. And then there's some trace stuff. And I was saying this about zipping, but I missed that we were actually calling apply fetch, which is the thing that actually fetches, which we defined here. Okay, and we've got these fetch to-dos, which is presumably like a to-do for the fetching. Okay. Let's look at wrap fetching. I'll look at the chat in just 1 second. So wrap fetch and catch exceptions arising from the data source and stuff them into the appropriate requests. We don't want any exceptions propagating directly from the data sources. Okay, that's good. At least that's what I want, because we want the exception to be thrown by the data fetch instead. Okay, so I don't know how you wrap a function in like try catch blocks. But you call it with rex and fetch, and if fetch is a sync fetch, I guess synchronous as opposed to async. Yeah, all right. Then we'll call sync fetch, applying this lambda rex goes to F of rex exception catch handler. Handler is down here. Okay. And if it's async fetch, then we've got rex IO goes to F rex IO, basically the same thing. Exception catch. This is a string, right? I don't know. It looks like a string. And then handler is a thing that takes some exception and returns an IO. And we're going to call rethrow async exceptions E. And then we're going to call map M underscore force error E on the rex. All right. Okay. And submit fetch return. Oh, sorry, I missed this, but you're saying it's maybe? I don't even see where the return, the type is. But yeah, it's probably maybe. All right. Well, so this is obviously well, not obviously. Obviously to me, less obviously to you, this is a flavor of Haskell that I'm not at all familiar with, because it includes a lot of things like different types of variables, the blocking and unblocking and async. This is stuff that I'm not familiar with. I certainly wouldn't know, as someone who has never developed Haskell professionally, I wouldn't know like which async or like var libraries are worth using or not worth using. I think it probably pays to be familiar with professional code bases like this, since they'll do all that research for you. But it's kind of coming together what's going on. I can sort of like make my way or muddle through the code. Here's the monad, which I think we've maybe seen some of. We saw right tree. Should we start from the top and read down? Here's run. Is there anything short? Let's get the short things out of the way. Okay, so run is pretty short. Stats is pretty short. So run run Haxl runs a Haxl computation in the given env. Note, to make multiple concurrent calls in run Haxl, each one must have a separate env. A single env must not be shared between multiple concurrent calls. Okay. Otherwise, deadlocks or worse will likely ensue. But it doesn't seem like they are. It doesn't seem like they're preventing that in any way by the by that. I'm laughing at bot user's comment. It doesn't seem like they're preventing with the type system. Yeah, I agree. I like C++ a lot. I think it's easier. But is it more fun? Is the question that I have. So run Haxl will call run Haxl with the env in the whatever a Haxl is. What is it? It's a gen Haxl thing, which I think we decide has some sort of number structure, but it's like a data type with just an unhaxl function or something. And we're going to call run Haxl with writes with the env in the Haxl. And we're going to call do result some ivar thing with some result reference. And we're going to call new ivar. I guess this is probably like calling new in C++, where to put the final result. And if there's a trace log, we're going to do some complicated stuff, which I will ignore. And if we're down here, it says run a job and put its result in the given ivar. So schedule will take an environment and a job list and a gen Haxl and an ivar and some logging stuff. And we're going to inline some stuff, inline result. We're going to read the IO ref. And if it's ivar full, an ivar is typically only meant to be written to once. So it would make sense to throw an error here, but there are legitimate use cases for writing several times. Okay. It seems like maybe you should use something that's not meant for single writing then. But at any rate, we're going to call reschedule env on the request if the ivar is full. If the ivar is empty, then we're going to write into it with the result. I don't really know where we got the result. At any rate, we're defining the result, I think, or a result of R. Have we got the final result now? We're going to try to unsafe coerce the result ref. And if that works, then if it's a, whatever an RQ is, we have a result, but don't discard unfinished computations in the run queue. So RQ is a run queue. So if it's a run queue of job nil, so there's, I guess, it's not done, then we're going to do some sort of appending to the job list. Otherwise, we're going to reschedule. I guess we're just checking the IO ref. Is that the only way we're getting seeing if the result is done? And then we just know that some other process is writing to it when it's done. And then if we're down here, if we have an exception, we're going to read through the exception. If we are done, then I saw done before. So maybe done is just marking a thing as done. Then we are going to write, I guess, into whatever the W is. I assume somehow we're doing some writing, and we'll send back result of okay, A, just whatever the thing we wrote was. And if it's right of a throw exception, I'm not sure what that's about. But again, we're going to go to read IO ref in the write logs ref. And possibly throw a Haxl exception. Maybe that means that we have gotten a successful, maybe that means we have successfully done the round trip. Like we talked to the server and the server told us to back off or something. So it's maybe not an exception in this sense, but it is something that we want to record that we successfully fetched an error or something along those lines, or we might be blocked. Okay. For reschedule, it says, here we have a choice. If the request store is non-empty, we could submit this request right away without waiting for more. This might be good for latency, especially if the data source doesn't support batching, or if batching is pessimal. To optimize the batch sizes, we want to execute as much as we can and only submit requests when we have no more computation to do. Okay, and this reschedule thing checks if things are job nils. If they are, we're going to get the queue. What? Maybe get a different queue and check that. And if this is checking if Haxl says job nil. So I guess Haxl's is itself can be multiple requests, or at least is some job request thing. And if we're down here, we're gonna we reschedule by just adding it back to the schedule, I think. Something like that. Run Haxl and unfinished request. Run Haxl returns immediately when the supplied computation has returned as a result. This doesn't necessarily mean that the whole computation graph has completed. However, in particular when using p_and and p_or, we might have created some data fetches that have not completed but weren't required because the other branch was subsumed. So now we're getting into the kind of logic structure that they implied that they had, well, not implied, that we saw bits and pieces of at the beginning, but we haven't, I don't think we've really seen yet, or maybe I'm just glossing over them. But somehow we can build up like different fetch jobs, I guess, using this logic structure. And it's saying like, fetch from Facebook.com or fetch from the like CDN of Facebook, and whichever returns first will suffice. We don't need to wait for both of them. And you can kind of build up some sort of structure like that. It is a research language. I haven't looked at how exceptions work in Haskell yet. I don't know. I think that they're like error is built in, so it I assume it's like implemented in the runtime essentially in C or C++. I guess they don't use C++, do they? Here's stats. I'm going to ignore stats. Profile. I'm going to ignore profile just to reduce the complexity since we're already very complex. Here's call graph. It's simple. You've got an empty call graph. You've got a main function used as the root of all function calls. Whatever a qual function is, qual function main. The type of a function call is a pair of qual functions. Represents an edge between a parent function call, which calls a child function in the cell graph. Okay, so it's a list. It's a graph. We're just keeping a structure of lists. And the call graph has the list structure and some sort of map from a qual function to text. I guess maybe this is just like qual function is essentially like a pointer to the function, and text is maybe its implementation. An edge list, which represents the dependencies between function calls. A qualified function. A function is just text. And I don't know what it means to be qualified, but I guess it means you can run it. So a qualified function has a module name, a function deriving EQ and ORD. Let's see how qual function is used. I think I misspelled it. I wrote qual function. No, I succeeded. How about in monad? With call graph, returns a version of the Haxl computation which records function calls in an edge list, which has the function call as graph. Okay, I don't know when you would use this. Let's see if we can find uses of with call graph. To text, like the with call graph called with a, I don't know. Data sources, this should be for modeling the data source. I'm thinking of this in terms of like fetching, like curling. but I think you can also do like database stuff. The class of data sources parameterized over the request type for the data source. Every data source must implement this class. The data source keeps track of its state by creating an instance of state key to map the request type to its state. In this case, the type of the state should probably be a reference type of some kind, such as IOREF. Okay, we've got a state. Blah, 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 blah. It's a class. We've got fetch. Issues a list of fetches to this data store. The blocked fetch objects contain both the request and the result vars. I was thinking blocked earlier. I was thinking blocked had to do with like things you were not allowed to fetch, but I think this is blocked fetches in the sense of like they haven't returned yet. They're blocked on some other request potentially. We've got states flags the user environment, and it's going to return a perform fetch of the request. See also perform fetch. You've got scheduler hint, which by default is try to batch. So I guess if you don't want to batch, you got to override it. You've got a scheduler hint state, the data source name, etc., etc. Scheduler hint try to batch, etc. Async with dispatch, stub fetch. These, whatever this is, some fetch template. Common implementation templates for fetch of data source. So async fetch with dispatch. It's a type that has whatever a service is. It has two IOs. It takes a service and an IO and returns an IO, a wrapper to perform an action in the context of a service. And dispatch all the pending requests, service to IO, and wait for the results, service to IO. Okay. And then for all A, given a service and a request of type A, we're going to basically do the request, right? And either return some exception or an A. Okay, and here's sync fetch. So these are like essentially templates, as they call them. But for example, async fetch with dispatch. You got this with service, dispatch. I mean, this is kind of cool. This is kind of like meta programming. You'd presumably in C++ do this with templates. I'm not going to dig too far into this because I'm kind of ready to almost be done, but I do want to see, I think I'm ready to see some examples. And in particular, I want to see if like they have like an example with a database. Facebook. Data source.hs. You've got some data source. Hash with salt. User token access. I don't know. This is harder to read that example than I wanted it to be. I really want to see the SQL example. Class SQL result, where we have some mock result. SQL name. So I guess they give you enough stuff to configure it. And it's I guess they don't really provide like an HTTP implementation or whatever. So they don't, So here they're defining a SQL query, select ID from IDs. Data source user rec, where fetch. Okay, so the fetch, we're defining what fetch does and the state and everything. And it's gonna take this SQL, which is called all IDs. And we're gonna call map m underscore. On all IDs. And unless IDs is null, we'll set the names to be calling SQL on unwords, which is kind of taking a list of strings and I think making a big string into them. Select from names where intercalate. So we're basically building up a SQL request here. I guess assuming the IDs came back, and then we're going to call map m on query put success. But are we actually making a call to SQL? I think this is just kind of mocked up. Mock result, Jim, text append. Okay, so this is like a mock SQL, but I guess kind of following that pattern, you can build up real SQL requests, if I understand correctly. And it should do things like batch them up. Data cache, I will ignore. Memo, I will ignore. monad we've looked at. Request store is small. A request store view is a request store of map, whatever type rep is, and blocked fetches. So it's a map. We can look up the type somehow and get a list of blocked fetches. And that's all a request is. A container for multiple blocked fetch objects. So we don't know which data we will be using. The store is dynamically typed. It maps the type ref of the request to the blocked fetches for that data source. Okay, so we've got dynamic typing, which is a real shame. It's a crime. Not really. Okay, and then this is just ways of handling it. We call add request. It's going to take a blocked fetch internal, which we saw before, a request store, and it's going to return a request store. So this should be like the existing store. This should be the store with the new stuff added. And we're going to call request store, and the request store needs a map. What map is it taking? It's taking the map that we get by taking somewhere there's a map we started with. We're going to call insert with combine whatever ty is of the blocked fetches. And the blocked fetches, I guess the constructor wants a list of BFs and BF internals. And the request store is parameterized by M, which is what? The like user environment, I guess. So really we're just inserting into the map that is undergirding the request store. And then combine in TY or here. So TY is some type ref dynamic typing stuff. Combine is a way of combining the blocked fetches, I guess, together. Okay. And then maybe block fetch internal is like the user didn't request those fetches, but maybe their fetches requested those fetches or something along those lines. And then run. I think we saw run a little bit. I'm certainly going to ignore it. And concurrent IO is what? 71 lines of code. And I'm just skimming for things that look promising. IO stay, concurrent IO rec. I don't know. I think mainly we're using control concurrent and like writing a wrapper around that. So that leaves us with monad and other monad. So let's look at monad. So here's the environment. We've got a data cache, memo cache, flags, user env, stats ref, prof current, just lots of stuff. States has a state store. Data sources and other components can store their state in here. Request store ref, submitted rec. So this has all the stuff, all the state. So this is big, like God state object. And init env with data. This is going to do some initialization. So for example, our queue, the run queue starts with job nil. The request store starts with no requests, and so on. It's like zeroing out all the memory. Okay, empty env, sanitize env. What does sanitize env do? If you're using env from a failed Haxl computation in a second Haxl computation, it is recommended to sanitize the env to remove all empty IVARs, especially if it's possible for the first Haxl computation could have been corrupted via an async exception. So like if it was interrupted. Okay. The right tree we saw a little bit. I don't think we're going to improve our lives by looking at it more closely right now. And here, maybe this is trying to tell me that this is what U, W, and A are. So it's a reader monad for env. I think it means that U stands for env. U stands for the user environment. W must stand for the right tree. Concurrency and resumption monad doesn't seem to correspond to A. But A should be the result type. I don't know how this ends up being integer-like in any way, or number-like. And then we have the definition of job list. which again has the environment, the gen Haxl stuff, and another job list. Whatever job cons is doing. Oh, I think this is just maybe, this is the thing that we're consing onto, perhaps. I don't know. Append to job list. We're calling job cons of all the things. And then we get job, and its implementation is we're going to job cons all the things, whatever. I guess this is a combination of dollar and eager. Recursively append to job list, etc. And if we're append to job list C with job nil, we just get C, and vice versa. And then here's some IVAR stuff. A synchronization point. It either contains a value or a list of computations waiting for that value. Okay. Add job panic. And we have result var. The contents of a full IVAR. We have to distinguish exceptions thrown in the IO monad from exceptions thrown in the Haxl monad. So when the result is fetched using get IVAR, we can throw the exception in the right way. And that might be similar to what I was saying before, but we have we have a throw Haxl and some throw IO. Where and those are different kinds of errors. Done seems to be just marking something as done. Return done of A. Either to result blah blah. A completed request from a data source containing the result and the IVAR representing the block computations. Okay. And then what is this big thing down here? It's a result. It's either done of type of the result type, or it's going to throw some exception, or it's blocked. And there's a continuation. Cons is the continuation. And I'm not going to look too closely at that, but I do want to know, the thing that I want to know now is like, how is the prelude related? I do have Gemini Cly, hopefully. Tell me about the prelude here. It looks like gen Haxls can be added and have a number structure. So first of all, I guess let's think about what that would mean. So if you have two gen Haxls, they have an environment, they have a write thing, and they have an answer type. You would think that if you're going to add them, they should have to have the same answer type and stuff, but I don't know. I don't know how you get a structure on them. Am I understanding this correctly? All right, it's going to read those and come back to me. Did we look carefully at core? Am I missing something in core? Let's see if we can grab one of these. Oh, I see. Oh, the answer type becomes gen Haxl bool. So if A is, okay. So if the return type is a number, and we're doing computations that both return a number, they don't have to have the same environment or the same writey thing. But if they both return numbers, then we can detect whether they are whether one is less than the other. Although I don't know how you're going to get a W, U or W back. So is left A2 defined here? Let's look. I think I did that wrong. No, I didn't. Okay. So if it's some applicative thing. Google, be faster. Okay. So lift the binary function to actions, and we need a thing that takes an A and a B to a C, and an f of a and an f of b, and we're going to produce an f of c. So I guess this is the binary operator. It takes two inputs and produces an output. And we are going to like applicify them. Some functors support an implementation of a lift A2 that is more blah, blah, blah. Do we get an example? So if we lift A2 of the comma to just 3 and just 5, it's going to return just 3, 5. If we lift A2 of the plus sign to these two lists, it will not add them. It will, yes, add them. Wait, no. We go up to 9, which is 6 plus 3. And the minimum is 4, which is 1 plus 4. We have more than 3 numbers. So is it 1 plus 4, 1 plus 5, 1 plus 6? Yeah. 5 plus 2. Okay. I wasn't expecting that. So in this case, A to B to C, the binary operation is plus. And given a list of ints and a list of ints, it is returning us a list of ints that have been added, but it's just returning more than I thought there would be. And I guess this is because the type here is list of int and not list of 3 ints. So if this is like a dependent type of 3 vector, then perhaps you could guarantee that you would get 3 back. But if there are no conditions on these being the same length, I guess it makes sense to just do the only thing you can do, which is just add them in like a loop, basically. Okay. I forgot that I'm using a customized version that is designed to verify that I was able to modify it. And so it's gone crazy. Okay, it has 3 instances. This means that if you have a gen Haxl that produces a numeric result, you can use standard arithmetic operators on it directly. So for example, if X is gen Haxl UW int, return 5, return 10. Yeah. So new type gen U Haxl. Yes, this is right. So UWA is a computation that will eventually produce a value of type A. So the U is for the custom user environment that you can define. So Gemini picked that up. Maybe it's documented somewhere. Maybe it just inferred it. The W is for a write log, which must be a monoid. Is that in the type? I'm not sure. This allows computations to log information. Okay. At its heart, a gen Haxl computation is a function. It takes an environment and returns an IO action that produces a result. The most important part is the result type. Data result UWA. Done of A, throw some exception for all, B blocked. This is the continuation thing that we saw before. Then the computation is finished. The computation failed with an exception or blocked. So while you can add them together like numbers, what you're doing is building up a larger computation that when run can be paused and resumed by the Haxl scheduler to automatically batch and parallelize data fetching. Okay, but so the result type of, what is it, plus is Haxl, gen Haxl something. How do we know that U and W is defined properly? Is my question even sensible? They both have to be environments, right? And they both have to be write logs. Suppose that I have A and B with different environments. So what can you say about the environment and write logs for A plus B? So it makes your job worse. But you know, to take your question seriously, what I assume that I just missed you asking that. Why is Haskell like this? Haskell is like this because I'm trying to think of the right way to put it. There is Lisp. I'm sure people have heard of Lisp. Lisp is closely related to a theory of, you might call it logic or computation, from back when they were trying to figure out what a computer was before they. Well, that's not quite true, but Lisp was done in like the 50s, but it's closely related to lambda calculus, which was done, I think, in the 30s by Alonzo Church, before we had really computers. And so there's this deep connection back in the kind of prehistory of computers between logic and theories of computation and programming languages, Lisp being one example. And Haskell is like a programming language that's closer to how somebody who writes programming languages might think, or somebody or it's closer to the kind of the logic of the underlying computation. And so that's basically it. It's a way to program a computer kind of using something that's closer to the language of logic, which is a nice to have as one of the tools in your tool belt, I guess, is one way to think of it. I guess Brahma was pointing out, it started as a research language. People do use it in production, but it's kind of like if you imagine like one of the old school logic languages, like Prolog, and made it nicer so that you could also like run web services with it. You'd get something a little bit like Haskell, something closer to the intermediate representation in compiler. That, I don't know if that's the case. That may be the case. The intermediate representation is often like a syntax tree. Let me ask the AI if there's a sense in which this is true. Let's ask ChatGPT because I think it might return faster. Is Haskell in some sense closer to the intermediate language in a compiler? I think that's not the wrong intuition. I think that's a good intuition. Yes, in some key senses, Haskell is closer to an intermediate representation. It separates the pure code from side effects, for example, I/O. Many compilers aim for similar purity to simplify reasoning, functional and compositional nature. They're often functional. Okay, yeah. So I think that's a good intuition. It's not perfect. People talk about things like function purity. That's also part of it. What that means is like in a Python function, you can do anything you want. Call out to the database or like erase the user's hard drive or whatever. In Haskell, the type system forces you to declare whether you're going to do like input output, and you can write, like if you for example at Google in a high quality code base, there's often guidance to try to make functions pure, like not depend on input output, and then the functions that do input and output, those are more specialized so that you can more easily test the pure functions and know what they're doing. But Haskell kind of makes that kind of discipline more mandatory, I guess. They right. A pure function that don't depend on state. Another way to say it is it should take the state. It should take the state explicitly. like a random number generator, for example, you should take the seed as an argument. And then the idea of the like IO in Haskell, like we saw a lot of things that are marked as having type IO of like result. That means that it's like taking the entire world as the state, including like, you can like look up what somebody's tweeting. You can look up you can look up an external random number generator. You can basically, the entire universe is kind of like the state, and you can't pass that explicitly. So that's kind of like an escape hatch is the idea. I asked an excellent and insightful question. I saw I was kissing your butt. Okay. You cannot, in fact, add two gen Haxl computations that have different user environment types or different write logs. It has been spoken. Okay, it'll prevent this at compile time. Okay, and that's, I guess, a property of lift A2. The function being used here is lift A2. Its general type is lift A2, applicative, blah, blah, blah. When we specialize this for gen Haxl in the plus operator, the applicative context is gen Haxl UW. Oh, okay, so this is sort of like currying. So this is one. Okay, so that answers my question. So you do have to have these be the same. That's fine. That's good. All right. So Buddy is asking why Haskell is like this, and it seems so hard. What are some benefits? I might as well ask to see if it's going to say anything better or more informative than I. The moment the AIs will be sincere with the stupidity of my questions, they will become a genius. I was just talking to my one of my kids about the importance of asking stupid questions. And I think somebody pointed out on Hacker News that it's easier to ask stupid questions of an AI, which I think is probably true. I probably feel about the same amount of shame asking an AI that I know is going to like track me for the rest of my life compared to asking a human. But I've for a long time been a big believer in asking stupid questions. I think it is true that for a lot of people, the AI will make that easier, and I think that's a good thing. AIs are not like all good, but I think that is one possibly good, one possibly good outcome. All right, you cannot. Wait, no, we already saw this one. It's a common sentiment. Haskell can feel like learning to sail on a different kind of sea. I guess it's saying that because I told it to call me captain. But the design that makes it difficult at first is also the source of its greatest strengths. I will perform a web search together. Okay. It has fewer bugs, high reliability. I guess this is an empirical question, whether it actually does have fewer bugs. You sort of see the same claim with Rust. In both cases, there are escape hatches, which is where you kind of move the bugs to the escape hatches. But this is one useful thing that I like strong static types, and I like the compiler to tell me if the code is thoroughly broken. And so like Haskell kind of does that to the nth degree. It avoids null pointers. You don't really need Haskell for that, but easier to maintain and refactor. You have to understand it, but this might be the case. Concurrency, expressive and concise code, and advanced features. All right, I guess that's good enough. We sailed the bugs to the border. Aye. All right, that's right. Okay, that's a look at Haxl. I am glad I did that. I don't think that I understood most of it, but I understood, I think, more of it than I had anticipated. And I think if I spend more time looking at some of these code bases, I'll develop a pretty good feel for how to use Haskell for real problems. Because something like this, where you are a company the size of Facebook and you need to do efficient fetches, that's a real problem. I don't know what they actually use this for. I'm guessing they don't use this, for like their main consumer apps. But that's an important function, an important piece of code, and hard to do, I think, even in a language like C++, where it's kind of easier to do this sort of thing. So that was fun. I hope you had fun. Thanks so much for joining me, and I'll see you guys again next week.